तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we had seen how dual supply arrangement can bias a transistor in the active region and how it can be used as a common emitter amplifier. Today, we will discuss an example in which the transistor is biased using a single supply. We already know how this can be made to work in the active region using a single supply. So, working out this example will further clarify how it can be used as a common emitter amplifier. Now, using a single supply, we had seen that we had to derive another supply from this single supply 10 volts. Okay. Another supply is derived using these two resistors 10K and 40K in this case as 10K divided by 10 plus 40K of 10 volts, that is the Thevenin's voltage, okay, which we call as VBB, which we have been calling. In this case, this comes out as 2 volts. And the Thevenin's resistance, which we have been calling as RB, which comes in series with these 2 volts, okay, is 10K parallel 40K, which is 8K. So, RB is 8K. That means I can now replace this circuit for DC. It will be exactly equivalent to a resistance of 8K in series with a battery of 2 volts. So, that is how we are able to forward bias the transistor, okay, by means of these 2 volts. We should in this case have an arrangement such that this 8K into beta plus 8K divided by beta plus 1 should be much less than 1.4K, that is 8K divided by beta plus 1 equal to should be much less than 1.4K, in order that we can neglect the DC drop that is occurring across 8K. This also we have seen. Let us assume for the transistor beta is, let us say, 99, we will take. Then in this case we have 8K divided by 100, okay, is definitely much less than 1.4K. So, this is valid assumption, right, or 8K is much less than 140K. Okay. So, this is valid. That means this can be neglected. The DC drop due to base current can be neglected, and this voltage can be assumed to be at 2 volts. Is this clear? So, now that we know that this is going to be at 2 volts, this is 0.6 volts VB. So, this voltage is 1.4 volts DC. So, 1.4 volts across 1.4 K gives a current of 1 milliampere. So, we know that IEQ is equal to 1 milliampere, because we have 1.4 volts across 1.4 K. So, now the operating point therefore is ICQ is equal to 0.9 that is 9 milliamperes, that is alpha, which is beta divided by beta plus 1, 99 by 99 plus 1, 0.99. So, alpha times IEQ, and VC equals 10 volts minus 6 K into 0.99 milliamperes. So, this voltage VC is going to be 10 minus 0.99 into 6, 10 okay. This is going to be very nearly equal to 4 volts, okay, or actually speaking, how much is it? 4.06 volts. So, this is at 2 volts, this is at 4 volts or 4.06 volts. So, VCB, which is an important VCBQ, is going to be equal to this 4.06 minus 2. So, we have fixed up the operating point, Q point of the transistor. I told you, measured in terms of ICQ and VCBQ. Forward, that it is forward biased is illustrated by the value of ICQ, okay. That it is reverse biased is illustrated by the value of VCBQ. Now, input resistance Ri. As far as the equivalent circuit is concerned, now we can put down the equivalent circuit of the entire amplifier. We have Vs with Rs of 1 K to ground. Let us go. This is called a coupling capacitor. Since this voltage is at 2 volts, I would like to decouple the signal from the DC. So, this is called a coupling capacitor. This will superimpose the signal over these 2 volts, okay, if I use this coupling capacitor. So, it will decouple the DC. Similarly, there is a coupling capacitor used to couple the actual load onto the collector. So, again this is because this is at a DC of 4.06 volts. This is going to decouple this. How does it happen? Because the capacitor here gets charged to 2 volts. Okay. This capacitor gets charged to 4.06 volts. Okay. So, that will automatically get charged to the DC voltage, and therefore, you get only the AC here. Similarly, this is automatically charged to this 2 volts. So, the signal voltage here is going to appear here, over and above the 2 volts. So, we have 2 volts, capacitor is a short circuit. Again, compared with what? always CC1 should be much greater than 1 over 2 pi f minimum into resistance coming across CC1. This is what we have used for CE also, design of CE. So, under the minimum frequency of interest, the capacitors should be so chosen that it is much greater than 1 over 2 pi f min r across CC1. That is done, it is a short circuit. Then we have 8K, and this is at a constant potential, and therefore, this is a short. Then we come to the base. Then we have RE, the small signal resistance of the transistor between base and emitter, and emitter is grounded through the capacitor, and we know how to select that value of capacitance. So, then we have the current source, dependent current source. If this is signal current IE, this current is going to be alpha times IE. So, we come to the collector point, this collector point. From here we have 6K to ground, because this is a constant voltage, and from that again we have a short circuit to another 6K. So, we have 6K parallel 6K. This is supposed to be the equivalent circuit of our amplifier. Is that clear? Now, if this is Vs and we have Rs, this we will call as, now instead of using all the symbols like delta, Vi and all that, we have agreed we will use this RMS value of voltages here, since most of this analysis is done for sinusoidal signals. We will use the RMS value of voltage, that is represented by V capital V small sub. So, input voltage here is V capital V divided by I, and the current here is II, which we have been earlier calling as delta IB, etc. II. So, similarly we will convert this into what? IE, and this one to RMS values I. So, this current here is going to be Vi divided by 8K, and this is Vi by Re. So, the total current II, this is nothing but Vi by II. Input resistance here is input voltage Vi divided by input current, that is the input resistance. So, II we will write in terms of Vi now. So, II is equal to, this current is this current plus this current minus this current. This current is in this direction. So, this current is Vi by 8K plus Vi by Re. Re is how much? It is operating at 1 milliampere. So, Re is equal to 26 ohms. 26 millivolts divided by 1 milliamperes. So, this is going to be 26 ohms okay, or we will write down everything in terms of ohms. V I by 26, okay, minus alpha times I e. What is I e? V I by R e. I e is equal to V I divided by R e. So, same thing, alpha times V I by 26. Alpha is already given as 0.99. So, this equation straight away gives us the input resistance. Actually, this is going to give you I by V I, therefore equals, okay, 1 over 8000 plus 1 over 26, okay, into 1 minus alpha, which is 0.01. Okay. Actually, therefore, this is equal to 1 over 8000 ohms in parallel with 1 over 2600 ohms. This is, okay, 1 by 26 into 1 minus 0.99, which is 0.01. Okay. So, you can see that R I is nothing but 2.6 K parallel 8 K. So many kilo ohms. How much is this? Please calculate this. This is about around 2 K. 1.95 K. So, that is the input resistance offered by our amplifier. Please note that it is 8 K, which is coming straight away here, and whatever is offered by the amplifier as 2.6 K. So, this 8 K is also taking away certain amount of the signal current. Actually, in order that this should not take any signal current, it should have been of the order of 10 times 2.6 K or so, 26 K. So, the design is not good, right. If you make it too high, then it will not satisfy this relationship. If you make it 26 K, it will not satisfy this relationship. So, this will no longer be a stable 2 volts. Okay. So, these are the compromises that are made in the design. Okay. Does not matter, some amount of signal is going to be lost, because this bias resistance is going to take away certain amount of current. Okay. So, what is now the gain? This also is over. Input resistance. Output resistance is very simple. You are looking at it from this side, that means you are looking at it, okay, from here, that is, this is the 6 K load and this is the collector point, okay, looking into the collector. So, this is a current source which is excited by the input. So, that current source is not at all there when you are exciting it by the output. Okay. So, just the 6 K resistance is going to be the output resistance. Right. So, output resistance is equal to 6 kilo ohms. Simple. Now, the voltage gain is nothing but V naught, which is this voltage, divided by V I. This is one voltage gain. What we are asked is V naught by V s. Now, that can be very neatly put down as V naught by V s is going to be V naught by V I into V I by V s. This is how we have been doing, right. V naught by V I into V I by V s. V I by V s, this is V naught by V I into, what is V I by V s? if this is Ri, Vi by, so Ri by Ri plus Rs. So Ri by Ri plus Rs, potential divider action, because this is Ri, we have replaced it by an equivalent input resistance. So Ri by Ri plus Rs is Vi by Vs. So it is left for us to determine V naught by Vi, because we know Ri is this 1.95 K and Rs is 1 K. So this is equal to V naught by Vi into 1.95 divided by 1.95 plus 1 K. Now what is V naught by Vi? This also we have already determined earlier, okay, but we will again illustrate. This 6K parallel 6K is 3K. So alpha IE into 3K is minus V naught. So minus V naught is equal to alpha IE into 3K. Is that clear? This is assumed as plus and this as minus. So alpha IE will produce plus here and minus here. So minus, okay, V naught is equal to alpha IE into 3K. And IE is already known as Vi divided by Re. So IE is equal to Vi divided by 26. So this is actually 3K means 3000. So we get V naught over Vi equal to, from that replacing IE by Vi by 26, okay, minus alpha 3000 divided by 26 or minus 0.99 into 3000 by 26. This is roughly, please calculate this, about 120. How much is it? 0.99 into 3000 by 26. 114. Okay, 114 minus. So that is the voltage gain. Now I would like to further add certain questions to this example, so that the complete design is understood by us. First of all, the CC1 and CC2 and CE. Okay. Let us now exactly determine how to evaluate the value of CC1, CC2, CE. Now, I just said that the reactance of all these capacitors should be much less than, okay, at the minimum frequency of interest, the resistance across. This is the basic design rule. When we say much less, we will say 1/10. The short circuit, okay, means the resistance offered by these reactances should be 1/10 the resistance seen by these reactances. Right. Now let us find out in each of these cases, okay, what this resistance is going to be. Let us assume that F minimum is 200 hertz. Okay. Then R across CC1 equals 1K, we can see this 1K, then nothing but the input resistance, right. So, 1 k plus R I, which we have already evaluated as 1 k plus 1.95 k. This we had already evaluated, correct? So, this should be 2.95 k, or the resistance seen by the capacitor should be less than 295 ohms, 1/10. We will take it as 1/10. Okay? The resistance actually seen across the capacitor is 2.95 k. The resistance offered by the capacitor at the minimum frequency of interest should be of the order of 1/10, let us say 295 ohms. That means 295 is equal to 1 over 2 pi f minimum into CC1. So, if the capacitor now offers a resistance which is 295 or less, we are happy. Okay? So, CC1 therefore is equal to 1 over 2 pi into 200 into 295. This will be 360,000 about. Yes, how much is it? 2.6 microfarads. Correct? That means if I use any capacitor greater than 2.6 microfarad, it is going to satisfy this. So, this is the design rule. Similarly, you can find out the value of CC2 as, let us do that without going into all these equations. We know 1 over 2 pi into 200 into, what is the effective resistance across this capacitor? 6 k plus output resistance, 6 k plus output resistance, which is 6 k. So, 12 k. That means the resistance offered by the capacitor should be less than 1.2 k. So, this is 6 k and this is 6 k. So, 12 k, 1/10 of that is 1.2 k. So, 1.2 k. So, how much is this? About 10 microfarad it will be. Larger than this obviously. Fine. 0.66 microfarad. This is about 1/4 this, because it is to offer only a resistance of 1200 ohms, whereas this has to offer about 300 ohms. Finally, CE. Once again, I would like to see the resistance across this capacitor. This we had already done it earlier. The resistance across this capacitor is 1.4 k parallel RE, which is 26 ohms. Then you come here 8 k parallel 1 k divided by beta plus 1. Okay. Effective resistance from here to ground is 8 k parallel 1 k, that divided by beta plus 1, because the relationship between this current and this current, they vary by a factor of beta plus 1. So, the resistance across CE is equal to 1.4 k parallel 26 ohms plus 8K parallel 1K divided by beta plus 1, that is 100. Okay. So, this is going to be equal to, in fact, this resistance 8K parallel 1K is 8 by 9K, that divided by 100. So, 8 by 9K, about 900 ohms, that, so this will be offering about 9 ohms. Okay. This is offering about 9 ohms, plus 26, 35 ohms. So, we can ignore the effect of 1.4K. So, this is about, okay, 35 ohms. Is this clear? 26 ohms plus 8K parallel 1K is, okay, 8000 by 9K, which is 900 ohms, that divided by 100, 9 ohms, 9 plus 26, okay, is 35. 35 parallel 1.4K is 35. Okay. So, roughly 35. You do not have to calculate these values exactly, because our selection of capacitor is always going to be the higher value, okay, than whatever is given. So, 35 ohms, that means this capacitor should act as a short circuit, okay, and that reactance corresponds to 3.5 ohms. Okay. So, Ce is equal to 1 over 2 pi F minimum into 3.5 ohms. So, somebody can calculate this. So, about 250 microfarads. How much is it? 227 microfarads. You will see that in a typical design, it is the highest capacitor that, okay, is costlier, right, than the other capacitors. So, this is the one which determines really what is called as lower cutoff frequency. Right. If they are not acting as short circuits, they will reduce the gain, okay, they will take away some voltage here, okay, and some voltage here. So, they will reduce the gain, and that will bring about a poor lower cutoff frequency. If this kind of design is done, it will assure that up to 200 hertz the gain is not reduced at all. So, these coupling capacitors bring about a lower cutoff frequency in the amplification factor. So, the amplification will not be 114, okay, up to very low frequencies, because it will be 114 up to about 200 hertz. Thereafter, it will come down to 0 as you approach the DC. So, that brings about a lower cutoff frequency. Therefore, the lower cutoff frequency in an amplifier is always determined by these capacitors. Okay. Now, you can select any one of the capacitors to determine the lower cutoff frequency exactly. Other capacitors are designed to be short circuits. Okay. So, that is the way design is done. Now, the final thing about this amplifier is that as you apply the signal, keep on applying the signal, this output will keep on getting amplified. Okay. This signal, let us say, is increasing. This is getting superimposed over 2 volts signal, but it is getting amplified by 114 or so, which is quite large. Now, essentially, therefore, you can consider that this is going to remain at 2 volts even when the signal is present, because this signal variation here is going to be very small compared to 2 volts. Right. Suppose it is 1 millivolt here, here it will be 114 millivolts. If it is 10 millivolts here, it will be 1.14 volts already this has gone up to volts range. Even then this voltage is remaining very nearly constant at 2 volts. So, basically you can assume for all practical purposes this is remaining unaltered at 2 volts. But this voltage is going to keep increasing and decreasing. When this is increasing, this will decrease. When this is decreasing, this will increase because of the phase shift. But now for large signal I can still assume that this voltage remains essentially constant at 2 volts. Now this voltage is changing from 4.06 volts. Suppose I apply 10 volts, this will be swinging from 4.06 okay, all the way down to 4.06 minus 1.14 and 4.06 plus 1.14 if it is assumed to be linear. Now I am asking you a question as to when will this go to saturation and when will it go to cutoff. So this is some question that you have to answer. How do we answer this? We know cutoff it reaches when IC becomes equal to 0, instantaneous value of current becomes equal to 0, which means the signal swing in collector current becomes equal to ICQ. This is always something that you can remember. If this is operating at 1 milliampere, obviously it can swing up to 2 milliamperes and 0 milliampere, around 1 milliampere. Okay? 1 milliampere plus 1 milliampere, 2 milliamperes, 1 milliampere minus 1 milliampere, 0 milliampere. So that 1 milliampere change may have been brought about by a disproportionate change here because of the nonlinearity. Okay? Now that is of no consequence. So this swing here, current swing, for it to go to cutoff is 1 milliampere. If it is 1 milliampere swing peak, that is flowing into a resistance combination of 6K into 6K parallel 6K, which is 3K. So the voltage swing possible before it goes to cutoff is 1 milliampere into 3K, which is 3 volts. So before it goes to cutoff, it can go to a swing of 3 volts. Is this clear? Now, as far as the other thing is concerned, instantaneous value of VCB should go to 0 when it goes to saturation. The actual VCBQ is 2.06 volts, 4.06 minus 2 volts. So the voltage swing possible here is, how much is it? 2.06. Okay, because when it goes from here, okay, down by an extent of 2.06, this potential will become same as this potential. Okay, so 2.06 volts is the swing on the other side. On this side, the swing is 3 volts. It is asymmetric. This is not a design problem where you have been asked to design the operating point such that it is symmetric swing. What it means is the amplifier goes to what? Saturation region. The transistor goes to saturation before it goes to cutoff. If you apply a sine wave, right, the first distortion that will appear in this case is due to what? Saturation. Okay. So this is important. This will not occur. Okay. It is this that is important. So this symmetric signal swing here is how much? 2.06 on either side, because here it can go as much as 3 volts. So it can easily go to 2.06. So the lower of these two will set the limit for symmetric swing at the output. Okay. So with this the complete discussion of common emitter amplifier is over. However, I would like to just say one thing. The characteristics of the transistor we have assumed as a current source, okay, alpha times IE. Okay. So, the equivalent circuit of the transistor is very simple, RE which is equal to VT by IEQ, and a current source. Please always put down this dependent current source IE. If it is, this is alpha times IE. This is the simplest equivalent circuit we have used so far. Another one simpler also we have used, wherein we just said this is a short circuit, okay, and if this is IE, that is alpha times IE. The simpler than that, which is nullator narrator one, we just said this is IE and alpha is equal to 1, okay, and there is no base current at all. Okay. So, that is the simplest equivalent circuit. So, what we said was this is a short circuit and this is alpha times IE, this is IE. This is simpler than this, right, and further we just said this is IE, this is IE, alpha equal to 1, the ideal transistor equivalent circuit. And you see here, if you represent this by an equivalent circuit like this, IE, if it is taken, IE is the current source current here. That means the current in this is always 0. Okay. Between these 2 points, potential is 0, the current here is 0, and therefore, these 2 points were replaced by what is called a nuller, because current through this is 0, okay, voltage across it is 0. That has been brought about by definition of an ideal transistor here. Okay. This is IE and this is IE, in which case only when this is IE, this current is going to be 0. Okay. Therefore, between these 2 points you represent it by a nuller, and here this is a narrator. This is a source which can give you any current, okay, across it, any voltage can be sustained. So, this is the route to the ideal network representation of a transistor. So, this is the base, this is the emitter. So, junction between this and collector and this is the emitter and this is the base. Through the base there is no current. So, you can therefore see the development of the equivalent circuit. In most of the non-ideal things we will use this equivalent circuit. In a very big circuit we can even use this nullator narrator equivalent. Is this understood now? This we had already discussed earlier. Now, I just want to modify this slightly and bring about a non-ideality. Yeah, this is not a current source which is ideal. There might be a large resistance of the order of tens of mega ohms across it, because it is a reverse bias junction. Collector based junction is a reverse bias junction. So, it is not a current source. Okay. There is a resistance, okay, which we will call as RC across this. So, please remember that this is a new thing that we have brought about here. Across collector base junction there is a resistance which is of the order of tens of mega ohms, which we have been earlier ignoring. What does this mean? That at any given operating point we had assumed that the characteristic is an independent, okay, it is independent of collector base voltage, but there is a dependence on collector base voltage for this current. That is why collector base voltage dependence comes about because of RC. Earlier it was a independent of the collector base reverse bias voltage, but there is a dependence on collector base voltage now. And this slope at any given point is what is called RC. This is a small signal resistance, which is RC is nothing but delta VCB divided by delta IC. Change in the collector base voltage for a change in collector current by definition at a certain operating point. This is typically of the order of tens of mega ohms. Let us try to learn more about this output resistance for this transistor, bipolar junction transistor. This effect that we are going to discuss is called Early's effect. What is it? We know that we will again take the same PNP transistor that we had used earlier. This is the emitter current. We have the collector receiving most of the emitted carriers at the collector, and very little of it is left as the base. Alpha typically is made very close to 1 when it is forward biased at the emitter base junction and reverse biased at the collector base junction. Now, the depletion layer width here keeps increasing as this voltage VBC keeps increasing. So, when this voltage VBC increases, the depletion layer width increases. Now, what happens? Of course, the field here will assist, it will increase, and it will assist these to fast come to this side. But first of all, these things have to come to this side. That does not depend upon the field. But what happens here is that because VBC increases, the base width decreases, and those holes which are injected onto the base, a larger number of these will get collected here. That means alpha is going to be coming closer to 1. So, now alpha depends upon VCB. That means alpha will become closer to 1, or IC is going to increase as VCB increases. This is what is called early effect. Is this clearly understood? Because the depletion layer width increases, the base transport factor is going to become closer to 1 as VCB increases. That means IC is going to increase, because IC is equal to alpha times IE. For the same IE, let us say earlier we said for a given IE, and this is VCB variation, this is going to remain constant at alpha times IE. If alpha is now going to increase as VCB increases because of early effect, then what you will see is going to be the effect like this. That means, actually speaking, in our sort of characteristic curve, right, if this is IC, for different VCB, and for all values of IE you are putting down here, these will go on increasing. Now, what happens because of early effect is this effect is going to be felt more at higher currents, and therefore, this whole characteristic can be expanded like this, and it will intersect at a particular point, and this is called early voltage. For the next current, it might be something like this, and all these things will intersect at a particular point in this axis, and that is called early voltage, or mathematically I can say IC is equal to alpha 0 times IE, which is the independent factor compared to VCB, is 1 plus VCB divided by VE, where VE is the early voltage. Okay. So, it is a factor dependent upon VCB. For an ideal transistor where this effect is not there, VE is infinity. Okay. So, IC is equal to alpha naught times IE. Otherwise, it is alpha naught is the alpha which is independent of VCB, okay, to 1 plus VCB dependent by VE. This voltage VE is called early voltage. So, once again I can draw the characteristic here clearly, show you this is VCB versus IC versus VCB for different values of IE. So, you will get something like this. You extend this is okay minus VE, okay, this is actually VBC, this is positive, okay, VBC is positive for P and P. So, for another transistor, another current, this is going to be the characteristics for a lower current. So, these are going to be extensions, otherwise actually characteristic is going to actual characteristic, because this is this region the transistor goes to saturation. So, this will be the actual characteristic of the transistor. So, these extensions join at a particular point, and that is an important voltage which is called early voltage. In a expression therefore, please remember, okay, you have to give this value if you want to see this effect of output impedance. So, output impedance is nothing but what? Delta VCB divided by delta IC. So, that is equal to, let us see, delta IC by delta VCB is nothing but from this expression alpha naught IE by VE. It is nothing but the coefficient of VCB. Okay. So, VE divided by alpha naught IE. So, given the early voltage as well as the operating current and alpha naught, you can find out the value of what? What is this? RC. So, this is an important small signal parameter. If you are therefore analyzing your circuit using SPICE programs etc., you have to give the early voltage. Now, I would like you to therefore compute the value of output impedance for the example, okay, that we have chosen, example 10. Okay. Determine the output resistance if RC is given as 1 mega ohms. Okay. RC is given as 1 mega ohms. Determine the output resistance now. Earlier output resistance was 6K for the example. Now, how much is it going to differ from 6K? Okay. You will see that it is not going to differ much from 6K in spite of the finite RC of 1 mega ohm. Okay. So, but you please use the equivalent circuit and find out for yourself. This will be worked out. Okay. This is a problem. Okay. This is problem. What is the number? 2. Determine the output impedance for example 10 if RC is equal to 1 MeO.